Hello, my name is Andrei and this is our KrakenBox, a deep learning-based error detector for industrial cyber physical systems, deployed on this small NVIDIA computer. When I connect it to a system, it starts learning the healthy behavior of the system. After that, it switches to error detection mode and uses the trained neural network in order to distinguish between the normal and abnormal system behavior. It is able to detect common errors of cyber-physical systems. Here, in this laptop, we have a Simulink model of two industrial robotic manipulators. They are currently busy emulating a production process. The KrakenBox is here, it is connected and trained. And now I will inject an offset into one of the sensors of this system using our UI. KrakenBox detects this error and signals about that. Now let's talk to the developer of this software.
Hello Shang, how are you today?
I'm fine, thank you.
Let's start with the Simulink model that we are using in our experiments. Can you say a few words about this Simulink model?
Yes, our Simulink models consist of two robotic manipulators. Both robots are moving balls, imitating the industrial manufacturing process. The control logic is implemented in Stateflow, and the robotic system is Simulink and SimScape. We adapt the model from masswork file exchanges.
Okay, so we have two virtual robots. Why we are not using the real ones?
It is because of flexibility. We can text and tune our method more flexibly using the virtual Simulink model. Currently, we are working on a real case study, but this will be the next step.
Okay, I see. Basically, we are sending some data from our Simulink model to our KrakenBox. Can you show what data we are sending?
Yes, inside one robot, we have 4 joints, and we are taking the first 3 joint position signal as our target. And we are sending this signal using UDP block.
I see. I also saw this UI on your screen. Can you tell about this graphic user interface?
Yes, this is our GUI to control the KrakenBox in this demo. We have 3 modes: training mode, manual fault injection mode, and automatic fault injection mode. In the training mode, the user can specify how much time he wants to simulate and how long it takes during one simulation. In the manual fault injection mode, the users can specify which sensor signal he wants to inject with which fault type, and he can switch on to inject. We can use the automatic fault injection mode. The user can specify which type, the probability, and the duration for each sensor signal, and click update, the fault will be automatically injected.
Okay, great, but can you tell how exactly we are injecting the errors into our signals?
We are using our fault injection block developed by Tagia. Now let's ask him about it.
Hi Tiger, how are you?
Hi Andre, I'm fine.
So can you tell a little bit more about this FI block?
Sure. Fault injection block, or FI block, is a new implementation of our model-based fault injection method. It is a custom Simulink block that is a masked subsystem containing MATLAB function block. FI block supports different types of fault, such as stacked, package drop, bias, bit flip, time delay, and noise, and also supports fault event parameters, such as failure probability, mean time to failure, or failure rate distribution. And also supports fault effects. It can inject faults once, at a constant time, infinite time, or using mean time to repair. When the user specifies fault type and parameters in the KrakenBox GUI, the KrakenBox calls specific functions at the FI block. It is also available as an open source tool on the GitHub and MathWork website.
Tiger, that sounds great. Now let's come back to our error detection.
Thank you.
Okay, Shank, let's talk a bit more about the error detection. Can you tell how we detect the errors?
Yes, here's our workflow for the detection. We follow the 5 steps: pre-processing, training, prediction, detection, and evaluation. At the beginning, we do the pre-processing, including resampling, standardization, with shaping, pretty much standard procedure when we do deep learning. The LSTM model is trained only on error-free data to learn normal time series patterns. At the same time, We tune our LSTM models by adjusting the hyperparameters to optimize it for prediction accuracy. After training, we do the prediction, detection, and evaluation. We basically predict the next single value and see how it deviates from the real one. If the residue is too high, we raise a red flag.
Okay, I see. But as far as I know, we could do error detection using several approaches, like classification, prediction, or even reconstruction. We follow the prediction approach. Why not classification?
Because prediction is better for the time series data. Plus, we can not only detect an error, but tell when it happens, localization. This can also be used for error mitigation as well for the classification of error type.
Why we are using actually LSTM but not some other neural network architecture?
Simply because LSTM is specifically suitable for time series data. It has no vanishing gradient.
Then can you tell me a little bit more about the hyperparameters of our LSTM and about the training process?
Yes. This is the parameter we use to train an LSTM predictor. We used a stack LSTM architecture with two consecutive hidden layers. And during training, we use a batch size equals 70 and Adam optimizer. We train our LSTM with 35 epochs with early stopping. Here we can see two consecutive hidden layers fully connected. In each layer, there is 50 cells for 50 time steps. In each cell, there is 80 neurons. And between the layers, there is a dropout with 0.3.
Okay, so look back 50 steps and look ahead 10 steps.
Yes.
So, okay, we do the prediction, but how we do the detection? I mean, yes, we are using the threshold, but how to choose a good threshold?
Yes, this is tricky, and it is usually omitted in most of the papers about prediction-based error detection. But this is a deep problem by itself. We recently published a paper where we compare two threshold setting methods, but this is still research in progress. Here, we just used fixed threshold for each sensor signal. I defined it using the Gaussian distribution method.
Shang, great. So now I think we can take a look how it works. So maybe we can start a system and inject some errors.
Okay, let's start the simulation.
And I see also on your video you already have your KrakenBox. Light is green, it means everything is fine up to now. Can you tell about the windows which I see on your screen?
Yes, here's a GUI for the KrakenBox software. It will show the data it received and the prediction result as an arrow with a red color. On the right side is 3D animation for the robotics system, and we have also showed the signals monitor.
These three signals which you have talked about, I see. Can we already inject errors or we need to wait a little bit?
Yes, we can already inject now. For example, we can inject offset at sensor 1.
Let's do it. Great, I see the detection.
Yes.
Can you inject some other type of error?
Yes. We can inject noise.
Okay, I observe the detection and it's almost immediate. Can you inject something into another sensor?
Yes, let's inject offset in sensor 3.
Let's try it. Great performance, Shang. Okay, Shang, thank you for the demonstration, and I think we can stop the simulation and take a look into the results.
Okay, let's stop the simulation.
Can you tell me what I'm looking at?
You can see 6 subplots. The black curve is signal value, and the blue curve is for the prediction. Red curve is for the residue between the prediction and the signal value. And the black horizontal line is the threshold. When it is above the threshold, we will raise a red flag, and we have show it with a vertical red span.
Okay, so we have 6 subplots, 2 subplots for each signal.
Yeah, for example, in the first sensor signal, we have injected an offset at around 10 seconds and a small noise around 14 seconds, and all of the errors are detected.
Okay, and on this protocol we could see basically the detection process, and now it is very transparent, so we can see when we have injected the errors and when we have them detected. Okay, Shonk, and what about the performance? How fast is the KrakenBox?
When it comes to real-time performance, we need to take two elements into consideration. The first is real-time measurement. For now, it's rather small network. So our challenge is at the second element, which is real-time response. We need to make a compromise between accuracy and reaction speed of the KrakenBox software. So we have made the model lightweighted, but still with an acceptable accuracy.
In our demonstration, we process 3 signals in real time. What is the sample time of each signal?
0.1 second.
Okay, so let's say we will detect error in 0.1 second. Looks good, Shonk. I would like to thank you for this demonstration, and that's great that you have shown some insight. Yeah, thank you and goodbye.
Thank you too. Goodbye.